Hello everyone, welcome to week 5 of the live tutorial for problem solving for structural analysis 1. So I am Prithvi Sangani. I am a research scholar from IIT Hyderabad. So this in this session, let us discuss about the deflection of frames, beams using unit load method, which is a virtual work method, and also the conjugate beam method. If you followed the last sessions, in the last session we discussed about the deflections of beams using moment area method and also using double integration method. So let us start the session. uh, First we'll take one problem on conjugate beam method, and then we'll solve a few problems, three or four problems using the unit load method, and we'll also take some frame problems so that it will be more helpful for us to understand the deflections in the frames also as well. So let us start with the first question. So the first question is, we have a continuous beam. We have a continuous beam with a hinge between roller supports and the overhang portion. So let us name this. This is B, this is C, D, E. Let us say this is F. So we have a point load 40 kilonewtons acting at B, point load 15 kilonewtons acting at F, and the spans are these are the spans. So AB is 10 meters, BC is 10 meters, CD 10 meters, DE is 15 meters, and EF is again 10 meters. So and also AC and also AC is having the moment of inertia as 2I, and the rest CD, DE, and EF is having moment of inertia as I. Alright. So so let us solve this question using conjugate beam method. So first let us know whether this is an determinate or an indeterminate beam. So by you can see here we have one the support at A, B, and C. We have again all the loadings, all the external loadings are vertical loadings. So we'll only have vertical reactions. So three unknowns. The equations of equilibrium are two. Those are in vertical direction, forces in the vertical direction, and the moments the sum of moments. But we also have an internal hinge here. So this is an internal hinge. So we'll have another equation coming from the hinge. The moment about the hinge is 0. So the sum of moments about the hinge is 0. So given structure is a determinate beam. Let us find the support reactions first. Okay, so reactions first. So let us take moment about hinge, that is sigma m about S0. Okay, so we have reaction force at A times 20. This is in clockwise direction, and we have 40 times 10. that is equal to 0. That implies reaction A is 20 kilonewtons. Next, coming to the next one, we have RE, right? So let us take yeah, again, moment about MC, but let us take this portion. Instead, we can directly do this. We can have moment about, let us take it D, okay, that is 0. So we have RA. So we already got RA. So RA is 20 kilonewtons. So let us find. So 20 times, how much is this? 30. 10 plus 10 plus 10, 30, minus 40 times 10 and 10, 20, minus RE. So I'm assuming RE as the reaction at E as upward. So RE times 15 plus, we also have 15, which is the external load. 15 times, how much is this? 25, and that should be equal to 0. So now RE, let us say this is 15 RE, that is equal to 600 minus 800 plus 15 times 25 is 375. So that implies RE will be 175 divided by 15, that is 11.67 kilometers. Right. Okay. So coming to RD, how do we find RD? So let us just take vertical forces in the vertical direction. Okay, let us take the forces in vertical equilibrate the forces in the vertical direction. So let us note down this in the question itself. So we have RE as how much? 11 point 11.67. 11.67. So RB, how do we find RB? So R, we have 20 because of RA plus 11.67. Let us assume RD also in vertical direction. That should be equal to the external loads. That is 40 plus 15. That implies RD can be found out as RD is nothing but 55 minus, this is 20 plus, yeah, 31.67. So RD is 23.33 kilometers. This is RD. This is RE. This is RA. Let me write down here. This is 23.33 kilometers. Right. So yeah, Suraj, just a second. Actually, I had some issues with the video. Yeah, I can continue. So, as I started this question, you can just note down the question. So, this is the question. We have a continuous beam A, C, D, E, and F. This is a continuous beam with an internal hinge. So, 40 kilonewtons and 50 kilonewtons are the external forces acting on the beam. So, I just started to find out the reactions of this beam, and the question is actually we need to find the slope at what to find actually the slope at A and deflection at let us find a deflection let us find deflection at C. Okay, this is the question. So we'll solve this. We'll solve this beam using the conjugate beam method. So initially I started working out the reactions of this beam. So the reactions are I have worked out the reactions as 20 kilonewtons. Um, yeah, the reactions are. Uh, Ganesh, can you unmute your audio? Yeah, yeah. Okay, thanks. So the reactions are so and so. You can see Ra is 20 kilonewtons, Rd is 23.33, Re is 11.67. So my next, yeah. So now we obtain the reaction. So what is conjugate beam? So what is so this is the real beam. Actually, the question which was given is a real beam. So what will be the conjugate beam for this? So first we need to draw the bending moment diagram, right? So let us draw the real beam again. So this is the beam which was given in the question. So A, D, E, we have an internal hinge at C. This is 40 kilonewtons. A, B, C, D, E, F. So this is the real beam. So what will be the conjugate beam for this? The conjugate beam will be if in a real beam if it is a pin support, right? So it is a pin support. The conjugate beam will also be a pin. Next, if there is a hinge in the real beam, then there is a roller in the conjugate beam. If there is a roller in the real beam, then it will be a hinge. Similarly, it will be that there's a hinge at E, and if it is a free end, then it is a fixed end. Okay, because the free end has both. The free end has both. You have a slope and also you have a displacement, right? So if you have a slope corresponds to shear force in the conjugate beam, and displacement corresponds to the bending moment in the conjugate beam, right? So obviously you'll have uh, both the shear force and bending moment. That means it's a fixed support. So first let us draw the bending moment diagram. So M by EI. So uh, the loading in the conjugate beam will be the M by EI diagram of the real beam. So let us draw the free body diagram first. So the free body diagram looks something like this. This is reaction A 20. So all the units are in kilonewtons. This is C. The reaction at D is 23.33. The reaction at E is again 11.67. There is an external force of 15 kilonewtons here, 15 and 15. So this is the free body diagram. What will be the bending moment diagram? So let us draw the bending moment diagram. I'll just draw the reference here. So yeah, now 20, and this is yeah, the dimensions as you know. Yeah, Ganesh, you have any doubt? All right, okay. So this is 10 meters, 10 meters, and this is 10 meters. This is 15 meters, and this is again 10 meters. This is not to the scale, so 10 meters, 10 meters, and yeah, 15 meters. So initial in the beam A, B, C, D, E, F. So in the portion A, B, the bending moment is positive, right? It is sagging moment, so we'll just write. So it is also varying linearly. So 20. Let us write what is the bending moment at B. B is like 20 times 100. That is 200. It's 200 here. Okay. When it comes to C, the bending moment should be zero. This is C, so the bending moment should be zero because this is hinge, internal hinge. Okay. Then what happens? Yeah. So what happens at let us go from support. I mean let us go from F towards E, D, and C. So it's up at F the bending moment is zero, and at E what will be the bending moment? 15 times 10, that is 150. So this is 200. I'm just writing 200 here. So this should be 50 somewhere here. This is 15 times. Okay, this is linear and it is 15 times 10. So I think you know why this is linear, right? So the minimum and anywhere here is 15 times x, so that is a linear equation, right? So this is 150, this is hogging again. And what happens at D? So bending moment at D, that is 15 times 25 minus 11.6 times 67 times 15. So that will be this will turn out to be 200. Okay, so let us again plot. This is 200. This would be linear, and at C it should be 0 because it is an internal hinge. Okay, so this is 0, 200, this is 200, and this is 150, and this is F. So this is our bending moment diagram. This is sagging positive, and all the way along C and F that will be negative. Okay, that will be hogging. So, sorry for that. Yeah. So this is positive and this is negative. All right. So this will be our bending moment diagram. But for the conjugate beam, the bending moment, the loading of the conjugate beam will be M by EI diagram of the real beam, right? So let us draw those. So let us draw the conjugate. Let us draw the conjugate beam again. So this is the conjugate beam and M by EI diagram. So here it is 200. This is A, B, C, D, E, and F. So at B, the bending moment is 200. But if you remember, if you have noted on the question, in the question we have given AC section is having mode of inertia as 2I, right? So that M by EI diagram will be 200 by 2 EI. That is 100 EI. So let us, this is 100 EI. And here it is 0. So here it is 0. Okay. This is 100 by EI. And let us come. This will be the same because CF has the moment of inertia as I itself. Oh yeah, you assume it as a linear. So this is 200 by EI. This is 150 by EI. And let us write down the supports also. So in a real beam, so what is the real in the real beam? The pin support will be the pin support. I mean the hinge support will be the hinge support, and the internal hinge will be a continuous support for a conjugate beam. This is real beam, this is a conjugate beam. Okay, the continuous support will be an internal hinge in a conjugate beam, and the free end will be a fixed end in a conjugate beam. So let us do the same thing. What about C? C is an internal hinge, so here it is. So this is internal hinge, and this is a fixed circuit. Okay. And what about the loading? Loading will be always away from the beam. So the loading is always away. This is something like a UV, not UV approach. Each span it is called uniformly varied loads. So let us note on this is A star, A dash, B dash, C dash, D dash, E dash, and F dash. So what is the question? Let us see the question. The question is find out the slope at A and deflection at C. So slope in the real beam will be the shear force in the conjugate beam, right? So shear force, now it was asked to find what is the slope at A. So now we need to just find out what is the reaction at A dash, right? Like what is the reaction at A dash? That will directly give us the slope in the real beam. So let us find out the reaction at A dash. How can we find that? Let us simply take yeah, we can take yeah, we can take moment about d dash as 0, and also moment about, okay, yeah, we can take moment about d dash as 0 and also moment about e dash as 0, because these are internal hinges. Let me write down internal hinge. Internal hinge. Okay. So yeah, let us start solving it. Now summation of moments about d dash by considering a dash and d dash, this span, that is 0. So I'm considering again the reaction at a dash as upwards. Let me just take it as upwards. So r a dash times this length 10, 10. This is also 10. I think this thing is 15. 15. Yeah, 10, 10, 10, 15, and 10. So this is 15 meters and this is 10 meters. So r a dash times 30 minus, so we have, or else, okay, or else however we have loading which is going upwards, right? Let us take r a dash as negative in the downwards direction. So in downwards direction, let us take r a dash times 30 minus, we have a triangular load, so that is half into 20. What is the height? 100 by ei. Now the center of gravity of this triangular load is again at 10 meters. So from d dash it is 20 meters distance. 20 plus rc, I'm bringing it downwards, rc dash times 10, plus we have one more, plus we have this coming downward, so that is of the same size of same sign of rc dash and ra dash. So I'll take it as half times 200 by ei times it is 10, yeah, 10 times 10 by 3. This is 10 by 3, 10 by 3, that should be equal to 0. So you just solve this equation, we will be getting something like this. RC dash should cancel 10 everywhere, so you 3a r1, that will be minus 3 r a dash, alright, and 10 will be cancelled everywhere, and then this 3 will be there, so we'll have plus 166.67 by ei. This is equation Just call this equation 1. Okay. Next, what is the other one? We can take moment about this 0 that we have done already. We can take moment about this as 0, which is e dash. So let us solve that. And e dash, considering a dash e dash. That's what I mean. So a dash e dash. So it should give the moment about e as 0. That in that case, let me just slightly. So in this case, what happens? R a dash times 10, 10, 10, and 15. So that is 30 plus, yeah, 45 minus half 100 by EI times 20 times 45 minus 10. That is 35 plus, let me write here, plus half 200 by EI. Yeah, 200 by EI is again downward, so it is plus 200 by EI times 10 divided by 15 plus again 10 by 3. Then what do we have again? Yeah, we have one more coming here because there is some kind of a trapezoid. You can see here there is some trapezoid load here. So let us divide it into triangular and then and also a rectangular load. So what we have, first rectangular load 150 by EI times 15 times 15 by 2, that is 7.5, plus half 200 minus 150, that is 50 by EI. This is with respect to the triangular loading. 15 times 2 by 3 times 15, that is 10, right? So that is 0. That should be 0. So if you solve this, you will be getting 45 RA dash plus 25 RC dash. That should be equal to minus 3958.33 by EI. Okay, this is equation 2. Now you can just solve these equations and you can find out what is RA dash. So RA dash will be 1520.83 by EI. So this is RA dash. What is RA dash? RA dash is nothing but the shear force at the shear force of the conjugate beam at support A. So now shear force of conjugate beam is not is equal to nothing, is nothing but the slope of the real beam. Okay. So now we have, if shear force is positive, right? So right now again the positive is something like this. So we have assumed RA to be negative downwards, right? So now we got it as positive. So if this is positive, which is downwards, right? If shear force is something downwards, then we have slope which is clockwise. If shear force is upwards, right? Shear force positive, so positive or upwards. So the slope is anti-clockwise. So now with this, how can you say what's happening in the video? Yeah. So the slope theta at A of real beam is nothing but 1520.83 EI clockwise. So how do we say that? So you can see here, this is the beam. What is the deformation diagram of this? Something like this. Sorry, something goes like this, and then you have a little bit downwards, and you have something like this. So this is theta. So you'll have this, and then you'll have a holding something like this. All right. This is theta. Theta is clockwise. And what is the other question? The question is deflection at C. So deflection, this deflection which. So I think I need to take a new page. Or else I'll just solve on this page. For this question, I'll just solve on this page. So deflection. What does the deflection mean? Deflection. So for the deflection, what we need to do? We need to find out the moment at C, right? So moment at C. So we already know RA. It is direct. So RA I already know. So moment at C. Sigma MC. How much? So that is going to be RA times 20 minus half times 100 by EI times 20 times 10. This is going to be MC. So RA we already know, 1520.83. 1520.83 times 20 by EI minus, I have this almost 10,000 by EI. So this is going to be this is 20 and how much is this? So 3000, this is 10, so this will be 10,000, so this will be 30,000 and something else. So 30,000 and something, or minus 10,000, that should be 20,416.67 by EI. Okay. So you remember this, if the shear force is positive, then the slope is anti-clockwise. So this is derived from the actual formula, right? We take upwards as, when you are deriving the beam, so this is positive, we have this is negative, and we take sagging as positive, sagging as positive and hogging as negative, right? So this is derived from this. So if shear force is positive, we have anti-clockwise, and if bending moment is positive, then this is upwards. The deflection is towards the top, which is upwards. So the deflection at C on the real beam is 20,416.67, which is upwards. Okay, let us go with the next question, and to take the new page, I think. Yeah. So this time I don't have a shortcut because I think let us go to the next question. So second question, let us solve curve beam with this, right? And we'll start using the unit load method. If you remember the unit load method, as we discussed earlier in the truss problems also, we have any beam. We have, let us say, some beam, something like this, and it is having some external loads P1, P2, P3, and we want to find what is the load or what is the displacement at C. Okay, so what do we do? For that, what we do is we'll take the same beam, we'll just remove the external loads. Instead, the point where we are interested to find the displacement, right? Let us say that the point is C. This point, we want to find displacement in this direction. Let us say this direction delta is how much. So we'll apply a unit load. That is one. So unit load, and then we'll find out the internal reactions or the internal displacements. So let us say this is internal reactions U. Because of this, internal reactions are nothing but the for the truss it is the internal forces. For the beam it will be the bending moment and the shear forces. But shear force, the deformations due to shear forces right now we assume it to be negligible. That's why the deformations from the bending moments will be assumed. It is actually negligible if you even consider the shear deformations, the deflections which you obtain after considering the deformations, those are negligible unless the beam is too deep or if it is again shear dominant kind of thing. So, anyways, in this case, we'll just find out. So, let us say this is DL and this is L. This is displacement inside. So, these are the strain displacements, right? So, because of external load, what are the internal displacements? And because of the external unit virtual load, so that virtual load will make it as 1. So this is something like this: 1 times delta is nothing but summation of U times dl. So if you are applying some virtual load P, that will be P times delta, but we want to find out delta, so that we will just substitute the virtual load P as 1, and that will be unit load. So 1 times delta is sigma U times dl, and delta will be equal to U times dl summation. So for each component, you'll find out what is U, and for each component, you'll find out what is the internal strains or the internal elongations, not the strains. So if you remember, for the truss elements, we are taking something like this. So sigma P K times L by AE. So P is internal forces, P L by AE is internal deformations or internal deformations because of the external applied loads. And what about the K? K is internal forces due to unit load, unit virtual load. Okay, so let us PKL by AE. So let us use the same concept when it comes to the beams, right? So when it comes to the beams, it will be something like this: integration mm by EI dx. So m by EI dx will give us the internal displacements due to the external applied loads, and small m, this the lowercase m, this will be internal forces, or in this case the internal forces are nothing but the bending moment. Internal forces or internal bending moment due to unit load. Let us use this concept and let us solve the problems. So the first question, yeah. So the first question is, we have a circular, like it's a quarter beam, something like this. So let us solve this. So this is given. This is A. Let us say this is B, and I'm applying a load of P vertical. Okay, this is load P acting vertically downwards, and what else is given? Yeah, this is a circular. It's a kind of a quarter circle. So this is radius R. That's it. This is what given, and what do we need to find? Find vertical displacement at joint B. Let us solve this question. How do we how do we solve this question? So now the vertical displacement at joint B has to be found out. We'll use the using unit load method. So we have the beam. This is the this is the actual beam. So let us call this as a real beam. So for this beam, let us find out what are the reactions. Okay, for this beam, the reactions will be, and just straight away writing down the reactions. So this is P into R. So you should have this PR, or you will have a PR in this direction, right? This is PR in this direction. Okay, the reaction force will be in this direction, and you have a vertical force of vertical reaction PR in this direction, upwards direction. So this is the reaction. So what all do we need? So the delta is nothing but the sigma m times n by di dx. Because this is the hint for this question. This is how you can find out. So we have only one member. Uh, Let us solve the question. This is the real beam P, and for the for the virtual load, what do we do? We'll take the real beam without any external loads. So the external loads P will be vanished. And what do we substitute in that? We'll substitute the unit load in the direction of interest. In the direction of interest. So what is the direction of our interest in here? So that is vertical displacement at B, right? So we'll apply vertical load 1 kilonewton or of any unit. So here it is given it as P and R, right? So let us say it's 1 unit. So one um, vertically down and applied at B. So this is virtual load. So now let us find out how do we find capital N. Let us take this section. So this section is at distance x. Okay, we can simply say it is P into x. So P times x. But now when we are doing the integrations, right, we should be very careful on how to choose what parameters or what are the independent variables that we are actually using in the integration, right? So this is theta. Let us call this as theta. Okay, so the x is nothing but this one. Okay, what about m? First we need what is m. So m is nothing but mx. That is nothing but p times x. That I can write this as this length as, I know this r, right? I know this r. So how can I write this? So I can write this as r sine theta. That is nothing but p times r sine theta. Okay, and and what about here? What about this? So we have again the same thing going on here. So we will have r, and this is one upwards. This is x. This is somewhere the same thing. This is theta. So dx, and this is nothing but d theta. And then this is d theta. So what happens again? This will be r sine theta, right? Again. So m will be r sine theta. That's it. So we have capital M, we have small m. Capital M is nothing but again, you need to follow. So this is delta is nothing but n by ei times m dx. So what is m? P r sine theta. Lowercase m is r sine theta. So dx, how do we find dx? Dx is r d theta, right? So we can write dx as, let us say, this is small part. So this is r, this is d theta, something with r d theta. Yeah. So this is length of the length of the curve is nothing but r times the angle subtended in between. Right? So this is r d theta divided by ei. So now what will be the lower bounds and upper bound of the integral? So the lower bound will be 0. My theta is varying something like 0 to, this is pi by 2. This is half, quarter, I was saying it as quarter. So this is 0 to pi by 2 r d theta. Once you do this, you will get obtain delta as p r cube sine square theta d theta by ei. So ei is constant in the question. So p r cube by ei integral sine square theta d theta. So now uh, how do we find integral sine square theta d theta? This can be written as what is cos 2 theta? Cos 2 theta is 1 minus cos 2 theta is cos square theta. Okay, let me just write it. Cos 2 theta is cos square theta minus sin square theta. I can write cos square theta as 1 minus sin square theta. So that will be 1 minus 2 sin square theta. So this will be nothing but this will go, so 1 minus cos 2 theta by 2 d theta. Now that is 0 to pi by 2. So that should be theta by 2 minus sine 2 theta by 4. So definitely right. So 0 to pi by 2, that that will be, that is equal to pi by 2 by 2, that is pi by 4, sine 2 into pi by 2 sine pi, that is 0, minus sine 0 is 0. Okay. So it is only pi by 4. So now the answer delta will be p r cube pi by 4 ei. This is very easy. So uh, this is one of the reason why usually energy methods are very powerful actually. So in this you can't I don't know whether we can use a moment area method in this. So if we try to use moment area method in this, that will be very complicated, right? You need to draw the Bellman diagram for this or any other movement. Let us say if you are using conjugate beam method, even that includes even it asks you to use the bending moment diagram, and you can draw the bending moment diagram, but it is always complicated. So you need to, that is one way, and that is one reason. And what about the double integration method? So if you use double integration method in this type of problem, yes, you can solve these questions, but you know that itself has a lot of um, complications, right? We will always develop a lot of complications in solving such kind of a curve kind of problem. So it's always better if you use energy methods or the virtual method, virtual load or the unit load methods for this kind of problem. So you can see here we can easily solve the deflections in curved beams using the energy methods. So I hope this is clear. This problem is clear. Let me go to the next problem. Let me see how much space is available. Okay, I don't have much space. Yeah, I'll take another. Let me take another question. Question 3. Yes. So let us solve one. Okay, next two questions. Let us solve beams or else let us solve one more beam question and then we'll go to frame questions. Okay. Let's solve one more beam questions and maybe the last question let us solve. Last two questions we'll solve the frame question. So this is question 3. So the question is something like this. So we have a beam. This is an overhang beam, simply supported overhang. We have at A, this is something like this, and at C, and CD is overhang. At B, the load is 30 kilonewton meters. Sorry, 30 kilonewton. A, B, C, D, and also C, and also at C, at A, we also have a moment already given. So this is the external moment. So maybe you have another beam going inside the plane from A, and that is giving you another moment, or you may have another beam which is going in another direction. So and that is uh, giving an external moment of about 120. So uh, how do we solve this? So let us solve for the displacement at D. Displacement at D. So this is a steel beam. So we have E as 200 gigapascals. I may be an ISMB beam, and the I is already given as 84.8 mm to the power 4. And the supports. The supports are 3 meters, 3 meters. This overhang portion is also 3 meters. So let us solve using uh, unit area method. Okay. So what do we need to do? So initially you find out uh, uh, capital M, and you find out what is the lowercase m, small m, and then you integrate, and then you find out the so reactions. Let us find out the reactions. Always we'll start with the reactions, right? So now I'm just writing down the reaction. So we have A, this is C. So how do we find the reaction at C? This is 30. So this is 120. So 120. Let me take reactions at 120 plus RA times 6 minus 30 times each 3, that is 0. So RA will be minus, right? So this should be minus, which is downwards 90 minus, this is minus 5. Because RA is not upwards, but RA is turned out to be downwards. That is quite, we can simply, we can even by the inspection, we can say, right? At A, you have a clockwise movement. So to resist that, you usually have reaction which is going downwards, unless you have too much external forces coming from the other directions. Anyways, this is which is coming downwards. What about RC? So RC RA plus RC is 30. That implies RC is 30 plus 5. That is 35. Should be plus. I'll just move on. This is sorry. This is 30. This is minus 5. And this is upwards 30. 35. Fine. Now we are done with this. So now what we are done with. We are almost with this with the support reactions. We can find out the capital N. So in each section we can find out what is the bending moment, right? And after that, what do we need to find? We need to find small m. Small m is nothing but the bending moment in each section or in the each span due to the unit virtual load. The unit virtual load acting at the point of interest. So at the point of interest is D, and we need displacement at D. So obviously we don't have any vertical displacement. We don't have any horizontal displacement. So we are talking about the vertical displacement at D. So vertical displacement at D. So we have A, C. This is 1 kilometer. So we don't have anything. So this is the real beam with virtual load, virtual unit load. So in this case, what happens? So we'll have you just find out. So we just 3 and 3 6. This is 6. This is 3. So this we can directly find out. Right? So this is 1. So this should be thrice. So this is downwards. This will be in tension 0.5 kilonewtons. This is upwards 1.5 kilonewtons. Okay, 1 times 9. So that is like this should be 3 uh, in the order of or in the ratios of 1 is to 3. Right? So anyways, so this is my reactions. We have A, A dash, B dash, C dash, and D dash. Okay, just dash is not something. This is not a conjugate. I'll just simply mention as A, B, C, D. Now I'll just make a neat table column. Or let us also break down into break down this into pivot diagrams. So M we have M. So let us write a neat table here. Span. Okay. We have length. Okay. Span. What I mean by span is A, B, B, C, and so on. So length. What is capital M? What is this small m? And di is constant. So what I'll do is dx. So let us find for all the cases. First, let us take for AB. So AB is span AB. How much is the length? Length is 3 meters. What is capital M? So capital M is this mx. So mx is it minus? Yeah, minus. Sorry, plus 120 minus 5 times x. Okay, this is 120 minus 5 times x. 120 minus 5x. What about m, small m? This is 0.5. This is in Hawking, right? So minus 0.5x. So the length, so how do we write this? So this is 120 minus 5x minus 0.5x dx by ei 0 to 3. Next, let's go with BC, span BC. Now what happens in span BC? So in span BC, let us say this. Okay, we have one 120, we have 5. So the shear uh, just right side of this. So just right side of this section, we have how much is this? 120, and 5 times 3 is 15. So that is something like 5 times 15, right? How much is that? So let us just break down. It's better. We will break down. So this is AB we have 125. So 120 and 5, this is 125, and you should have a sagging moment, right? So a sagging moment of about 5 times 6, no, what is this? 3, 15. 120 minus 5 times 3, 15. So this is 105, and you have a shear force 5. So when you take this, you have 30 kilonewton external force. You have 5 here, and you have 105, something like this. Okay, so this you can write it as BC is length 3, length 3, and you also have 105, 105 times 10. This is in what is this? This is sagging, right? 105 sagging. 105 minus 105, 30 downwards and 5 upwards, right? So we have minus 25x. Okay, and what about BC? And what about small m? So for small m, again, you break there. So you have zero point 0.5 downwards. So 0.5, so it's 0.5, but you should also consider the movement, right? So 0.5 times 3 is 1.5. So this is 1.5. Okay. So how do you write that? So that is something like this. So 0.5, that is minus 0.5x plus 1.5. Now how do you write this? 0 to 3, 105 minus 25x times minus 0.5x plus 1.5 divided by EI. So EI is again constant. What happens in CD? Let us take CD. So CD is again, this is actually, you can go from DC also, right? So DC there is no moment. So when you consider capital M, it is 0 directly. What I mean to say is, see here you have reaction from this direction, you just consider. So there is always 0 moment, right? There is no load there, so there's no point of finding out M. Anyways, I just want to find out M, and how can I do it? So 1 times 3, that is minus 3. So 1 into x is minus x, but that is minus. It is 0 times minus x dx by ei. So how do you find delta? Delta is nothing but the summation of mm dx by ei. You integrate all these terms, this should be 0. So you integrate this one and this one and divide it by ei, you will get delta. So I just solve this one and write down the answer. Maybe you can check it later. That is like 562.5 by ei. So in this, I'm getting delta as minus. So what does that mean? So minus, I have assumed delta to be positive downwards, right? So this is positive, which is downwards, but I'm getting minus. That means the delta is upwards. The deflection is actually upwards. So delta 562.5. So again, you need to mind the units correctly. So moment I have taken it as kilonewton, right? So, kilonewton meter. So let us write it as Newton and also meter as mm. And dx we have again, that is also meter. And we have dx, yeah. So we have dx times x. So that is like 10 to the power cube, right? Cube is 10 to the power 9 meter cube. EI. So what is E? I want to take E. I'll just tell you how these units. Let me let me tell you. So you have movement kilonewton meter. You have another movement which is kilonewton meter. You have dx which is meter. So kilonewton meter, kilonewton meter, that is kilonewton square, right? But you should also remember you have 1 times delta. This is nothing but unit load. This is kilonewton. So that kilonewton gets cancelled. So you have minus 562.5 EI. Let me write kilonewton. It should be kilonewton square, but this kilonewton square and this kilonewton and this kilonewton, 1 kilonewton is cancelled. Kilonewton times meter, meter, and meter, meter cube. Most of the students get this confused here. Right? So minus 562.5. Let me take newtons and this is meter cube. Meter cube is 10 to the power 9 mm cube. What about EI? E is 200 gigapascals. So 200 gigapascals is 200 into 10 to the power 3 megapascals. Megapascals is Newton per mm square. That is what we are doing. Yes, that is right. And I is given as 84.8. 84.8. So this turns out to be minus 33.2 mm. This is outwards. So that is quite evidential, right? So we can, when you are applying a load something like this, so you have deformations like this. This turns out to be 32.3 m, 33.2 m. Okay, this is again another easy problem. The reason why I choose this problem is how to actually find out the bending moments in each spans. Right? When we have a continuous span, we need to break down it and we need to find the free body diagram. From the free body diagram, we need to find out what will be the bending moment in each span. So capital M and the lowercase m, small m, and then you just multiply it, divide it by EI into dx, integrate it, and the sum of it will give you the deflections. This is about the question 3. Let us, yes, yes, yes. Yeah, minus 1.5. Let me check. We have zero point 0.5 here. So this is in this direction. So you'll have this is 1.5. This is 1.5. That is correct, right? It is plus 1.5. which can you tell me? Can you repeat again? Yeah, yeah. 4 meters span at point. Okay. Okay. But see, this equation is valid for only BC, right? We are only writing the moment equation for BC. So you are able to understand, right? So let us say if I am finding out at BC, let us say this is BC. You have a moment of. I'm only writing the moment Benny moment equation for BC span only. I'm just breaking it down and then I'm writing it because that in that way it will be easy for me to just integrate from 0 to 3. The span is BC, so that is 3 meters length. Okay, was clockwise. This is yeah. You're right. You're right. So this is clockwise. So you'll have an anti-clockwise. So, yeah, in that case, yeah, it is minus. Right. You're right. Yes. Yeah, it is clockwise. Then you'll have a reaction of anti-clockwise, and when you draw a free body, that will be again that should be. Yes, but anyways, you need to remember that we are only writing the Benjamin diagram or Benjamin equation for only each span. So it is basic and that thing. So that our calculations will be easy. We can easily find out from 0 to that spans. We'll just uh, we'll just break the beam into different spans, and then we'll write down the Benjamin diagram as our Benjamin equations. Yeah. Let me go to the next question. So that is question 4. Let us solve two frame questions. I think we have some time. I think almost we have 40 minutes. Let us solve frame questions. This is question 4. Yeah. So we have a frame something like this. A, B, and C. This is a UDL of 24 kilonewton per meter, and does not have any. BC does not have any load. Let us let it as 3 meters, and this will be 2.4 meters. So this is the question, and what is required? Horizontal displacement at point C. Find horizontal displacement of point C. So we need to find the horizontal displacement of point C. Obviously, there will be some horizontal displacement because we have the horizontal external load of horizontal external UDL of 64 kilonewton meter, and that will actually push this the ruler support at C, and will obviously get some horizontal displacement there, and that also gets rotated, and we'll also get some rotations at A. We'll also get some rotations at B, but that is not our point of interest. The question is to find out the horizontal displacements at point C. So let us use unit load method. Using unit load method. No. Uh, yes. Yeah, I remember discussing the same thing last time. If you remember, this is a rigid one, right? So this is a rigid connection or the rigid joint, right? So when you push this thing in this direction, right? So this will actually act in such a way that this can move forward like this, but then it will rotate, and then the moments will be taken by this one. So you'll have something like this. It will. You're able to understand, right? So like for example, if this is a hinged one, this is not rigid support. Sorry, I just messed up this. Just one second. If this part is not rigid, if this part is not rigid, if joint B is not rigid, then if it is hinged, if not rigid, then it is an internal hinge. Then, like you said, yes, this will just collapse and it just moves, and then there's it will just get collapsed. So even if you find out ds, right, ds is 0 in this case, and when you have a hinge, ds will be -1. So if it is less than 0, so you will have an instability there. Okay. Yeah. So yeah, find the horizontal displacement of point C. Maybe later you can also try that for the same question. You can also try what is the rotation at B. So for the rotation, you need to apply a unit moment of 1 kilometer meter. Anyways, let us solve for this question first. So again, we'll use. So this is the equation which we are going to use: m by ei dx. So the ranging from 0 to whatever the length is. So we'll just sum it for each span. So first, let us find out the support reactions. So Ra times, let us take the moment at C as 0, Ra times, this is vertical, Ra times 2.4 and minus 64 times 3 times 1.5. That's it. That is 0. But what happens if it is 0? That is 0. What do we get? Ra as 64, 3, 1.5, 2.4. 240, 150, is it 112.5 kilonewtons. Okay, RA is 1.2. I have already solved it, so that's why I'm just writing down the values here. So RA is 112, which is upwards. What about R horizontal? We also have a horizontal reaction, right, at RA. So that is again balanced by the external load. So HA, horizontal reaction at A, is nothing but 64 times 3, 12, 18, 1. Is it 64 or 60? Maybe I made it. Okay, yeah. I think I have calculated for 60. I have calculated for 60. Please just change the question. This is 60 kilonewton per meter. Yeah. So you'll get as 60 times 3 to 1.3. This is 60. So this will be around 2.5. 60 times 3 is 180. We can also take 64, but already have the solved. I have solved this question for 60 by taking 60 kilonewton per meter. So let us just just for the clarity and also for the confirmation of our answers, it's better we go for the ones which I have already solved. So let us take 60 kilonewton per meter. So our HA will be 60. That is already balanced by the external loads. So let me just this is upwards 2.5. This is this way. This is 180. Okay, that's it. So we have this we have done. So let us take the virtual load. So the virtual load, this is a roller support. I'll give a virtual load of 1 kilometer here. So what happens if I give a virtual of 1 kilometer? I'll get a reaction 1 in this direction, so this should be 1 here, that has to balance. And also this is rotating in this direction, so it has to counter in this direction. So 1 times 2 point, this should be 1 times, okay, let me write down, 1 times 3, that should counter x times 2.4. X is nothing but 3 by 2.4. What is it? 30 by 60. This is 1.25. 10 by 8. 5 by 4. Yeah, 1.25. This is 1.25. This is downwards 1.25. Yeah, the problem is almost solved. So this is A. What it is? Yeah, this is B, and this is C. So let us take now. What do we have? Span, length, span length, and span length. We have capital M. That is the moments because of the external loads, the real loads, and the small m, the moment in the span because of the unit virtual load, mm by ei dx. So let us take first, what is the span one? First span is AB. So for AB, length is 3 meters, 3.0 meters. So what is M? How do I take M? This is M, right? So M, what I'll do is I'll take, this is side, okay? So 180 is minus in this case, right? So 180 into x is plus. This is sorry, what? That is 180 into x, that is sagging, and this is hogging. So 180 into x minus 60 into x by 2. This is x into x by 2. That will be 60 into x by 2. That is 30x squared. 30x squared. What about small m? Small m is this. This is again sagging, right? So this is 1 times x, 1 times x. This is x. So it is ranging from 0 to length 3. 180 x minus 30 x square times x by ei dx. Now next BC. In other, I just want to skip finding out my bending moments or the shear forces here. Instead, I'll take from C, from this side, from this side. So what do I have? For C, it should be 112.5. So in this direction, so this is hogging minus 1, right? 2.4. This is minus 112.5 times x. And what about small m? This is plus 1.25 times x. 0 to, no, it is 2.4. Integrate minus 112.5 x times 1.25 times x divided by ei dx. Let us once check this. So this is moving this in this direction, and this moving in this direction. Yeah, this should be positive. And also when we consider this is rotating in this direction, but I think I have made a mistake here. Yeah, in this equation, this should not be towards up, right? Because see, in this equation, this should you have a rotating moment in this direction, that is, this is going to, sorry, so this is going to rotate this in this direction, so this has to be upwards, right? So if this is upwards, then this should be downwards. I made a mistake actually. So you can see this is rotating in this direction and this is rotating in the opposite direction. Is it correct? At support C, the reaction should be upwards, right? At support C, the reaction should be upwards. You can see here, this is rotating A in this direction, and this has to counter and it should rotate in this direction. Yeah. So this is 112.5. This is plus. This is plus. So once you do this calculation, once you just do this calculation, what happens is you will get delta as, you do this, just call this as 1, so delta is nothing but 1 plus 2, that is 1660.5 by EI positive. That means it is going in this direction. I have assumed, I have taken my unit load in horizontally right side, that is positive, so I will get my final displacement as positive in right direction. I hope this is clear. This question is clear. This is okay. But if it is upwards, right? Yeah. True. Okay. But yeah, yeah. See, we made a okay. In this, actually, we made a blunder. See, you can see this. We also have horizontal reaction in A, right? Yeah, yeah. That will actually compensate that. So it's better you take a moment at A as zero initially, and you find out vertical reaction at C. You're able to understand. Yeah, that we missed out. Yeah, initially even I missed out, but later I kind of somehow I just, so see, you usually, yeah, usually when you are instead of cycling hogging, like I think we both discussed earlier, right? So we are taking it as positive tension side and compression side, right? So that is how usually we define. But in the initial days, like before for the second years, third years, getting that in mind is kind of difficult. So that's why we usually call it as signing hobby. But otherwise, it is always taken as tension, tension. The direction, like the portion where we have tension, we'll take it as upwards and then downwards as compression. That's what usually the thing is. Yeah, yeah. But like once you keep practicing, we'll understand actually. Instead of directly saying it is signing or hogging, we can directly visualize like in which direction the beam is going to bend, and we can simply draw the maneuver diagram, and then we can also have that deformation diagrams and deformation profiles and so on. But yeah, So let us solve one more frame equation. I have solved it. So searching for it. Yeah. Similar kind of frame we have. This is kind of a cantilever frame. So I think we don't have enough space. Yeah. I'll just question 5. So this is a cantilever frame, but we also have. Yeah. So this is the loading profile. A, B, C. This is 8 kilonewton per meter, and this is 4 kilonewton per meter. The lengths are something like this. This is 9 meters. This is 6 meters. Just a second, I'll have some water. Okay, so what do we need to find? We need to find the deflection at C. We can have both horizontal and vertical deflection at C. Let us just find the vertical deflection at C first. Delta is how much? EI is constant. So again, similarly, like first let us find out the reactions. As this is a cantilever, we will have so this is I'm just writing down the resultant. This is not uh, we can't simply substitute the point load for the UDL. I'm just writing this is the resultant of this UDL. So 4 times 624, and we have 8 times 72. So these are the resultants. So 24 times 6 and 72 times 4.5. That is very huge, right? So you will have, so this is going to be a clockwise, so it develops an anti-clockwise response. So that will be, this is 24 times 3 plus 72 times 4.5. 72, 72, 4, 370, 396. This is 396. We'll also have a vertical force of 72, and you'll also have a vertical compressive force of 24. Now let me write down the loading. This is 8, this is 4. Okay, this we have found out. Now what do we need to find? So for the real, we need vertical displacement at C. So vertical displacement at C, for the vertical displacement at C, what I just find out is, so vertical, I'll apply a unit vertical load. Just but we know that it will be deflecting downwards, but let me just apply a unit load upwards. Just see what happens. Maybe obviously we'll get an answer in terms of minus negative values. Let us see what happens. So this is unit vertical load upwards. So this will generate a anti-clockwise movement. So you will have an clockwise response. 1 times 9, so this is 9. And you will have downwards 1. This is A, B, C, A, B, C. Right. Then this is for capital M. This is for small m. So let me take, let us uh, let us take A B span in both the sections. Let me write down span length capital M small m and m by EI dx. So we have something like this. Span is, let us say, AB. Length is 9 meters, 9.50. Capital M. So let us find out what is capital M. So we have 396 hogging minus 396. Next, 72. This gives us a sign. So plus 72x, and we also have a UDL of how much? 8, right? So 8, that gives an hogging value. So minus 8 into x into x by 2, that is 4x square. 4x square. Okay, yeah. What about this? So this is, oh, here the sign. So 9 is a sign value. So this is 9 positive, and 1 uses an hogging value. So 9 minus x. Integrate 72x minus 4x square minus 396 multiplied by 9 minus x by EI x 0 to 9. This is 1. What about B? The span is 6 meters. BC is actually quite direct. This is 0, right? The moment in BC is 0 when you have for a virtual load of 1. But just for the sake of problem, let us solve the pen moment in capital M. So the capital M will be now minus 4 into x into x, so that is 2x square. Minus 2x square. This is 0. So this entire thing will be 0. So only this will be the answer. 1 times delta is 0 to 9, 72x minus 4x square minus 396 times 9 minus x by EI dx. So delta will be, so I got it as minus 9477 by EI. I got it as negative. That means, yeah, the assumed direction is opposite of what the answer is. So that means the deflection is downwards, 9477 downwards. Let us also find the horizontal reaction, horizontal displacement or horizontal deflection at C. For the same question, let us also find the horizontal displacement. Delta H is how much? So my capital M's will be the same. There's no change in it. Only the small n changes. So let me try the B again, the frame again. This is 1. I'm assuming right side. So 1. So one time this is rotating in anti-clockwise. We will develop again clockwise movement. Yeah. 1 times 6. So this should be 6. There's no vertical force. So this is 1. So there is a tensile force in beam AB. Tensile force in beam AB. So I don't think I can copy anything. Right, the same thing. I'll just I'm writing this in another thing. So N for horizontal. What happens here? Capital M remains the same because the real beam is the same. So I'm not changing anything in the real beam. When it comes to this the small m, so small m, in AB, this is sagging. 6 is sagging. Okay, all right. Okay, just again for the sake of explanation, I'll just take AB. This is 6. This is 1. So usually what we assume is this as positive, right? Mx. So mx minus 6 plus 0 is equal to 0. Mx is 6. So that's the reason why I'm actually writing positive here. Okay, that is the reason why we are taking that as a positive sign. So this is 6. Oops, sorry. I'll share it again once. Yeah. Minus x, sorry, 6. 6 itself, right? There's a constant value movement there. There's no effect of the reaction forces because it is horizontal. So you only have an axial tension coming in the beam. What about BC? In BC, you will have something that BC. Uh, Again, you can see in this case, it is bending in this direction, right? In this case, it is bending in this. This is actually trying to bend in something like this. So, but in this, it is actually going in this. Okay. Anyways, we'll also formulate how it is. So if it is in this direction, again you have an anti-clockwise response in this direction, right? So that is again, it is hugging, right? It's hugging. Then you have in this direction, you will have a, yeah. So similarly, what happens in this? So you have, it is rotating this in this direction, and you have clockwise movement generated. So that is opposite of what's happening there. So it's positive. So what I'll write is 2 times x. This is x, only x. So if you want to find the horizontal reaction, uh, so sorry, horizontal displacement, delta horizontal is, this is again delta vertical. I just rewrite again. 72 72x minus 396 minus 4x square divided by ei into 6. This is running from 0 to 9, plus one is minus 2x square and one is x, minus 2x square times x divided by ei into dx. This is running from 0 to 6. This direction is, yeah. This will give us the horizontal displacement. So this I didn't find out. You can find out. You can just find out how much is the horizontal displacement in this case. So this is about the unit load method. How we use the unit load method to easily solve some complicated determinate structures. I think from the next week onwards, we'll be discussing about how to solve the indeterminate structures. If you can just observe, for till this week we have solved for deflections and finding out the internal forces, shear force diagrams, internal forces, drawing shear force diagrams, bending moment diagrams, and deformation diagrams, and also the deflections using various methods, and all these things, all the so all these methods we have applied for the determinate structures. So now what if and how to analyze the indeterminate structures, I think we'll be discussing from the next week onwards.